Hello. In this video, we're going to show how to construct semi-analytic solutions for spontaneous imbibition. And it's semi-analytic. We're not actually going to write down a fancy function like an error function for the solution, but it basically enables you to find solutions to the equation with arbitrary accuracy. But let's at least specify what it is we're doing. So the partial differential equation we're going to solve is as follows. There's a time derivative here and there's a spatial derivative here, but Q is driven by spontaneous imbibition and it's minus d ds dx, and d is our capillary dispersion or diffusion coefficient, and it's got these two mobilities. It's got an absolute permeability, and then it's a derivative of my capillary pressure. And there is, don't worry too much about the minus signs, this derivative is negative, so d is strictly either 0 or positive. Okay, now let's at least introduce the boundary conditions. So if we consider a capillary pressure curve, and I do it, we imagine that we start with some initial saturation, which is your irreducible saturation where there's no flow, and then we imbibe its spontaneous imbibition. So we don't drive the saturation all the way down to a residual, which we do if we're pushing one phase in, say we're pushing water. We can only imbibe to where PC is 0 because it's spontaneous imbibition, and we call the saturation at which this occurs S star. So now we're going to look at a one-dimensional displacement like this, where one phase and its water moves in, the other phase moves out, so it's counter current. The total velocity is actually 0. The initial condition is that S1 is the initial immobile saturation, and at the inlet, and this is x, at x equals 0, we impose this saturation or capillary pressure of 0. So this is S1 star here. So that's the initial condition. This is the boundary condition. Okay, now let's go through some of the mathematics. So the first thing we're going to do, right, it's a diffusion problem. We've done this for heat transport. So the first thing we're going to do is, why don't we try a diffusive type behavior? We're going to introduce our omega variable again, which is x over root t. Okay, so we've done this before, so I don't want to dwell on it too much, but let's see where it gets us. Right, so let's try and at least do it properly. To begin with, I'm just going to keep the q in, and there's a good reason for that. So I'm going to write dq1 by dx is going to be dq by d omega, okay, d omega by dx, and that's going to be easy. That's just 1 over root t. So that's shouldn't be too difficult there. And then the ds by dt term is ds by d omega, and then d omega by dt. Okay, and this one we may need to think about it a little bit more, but it shouldn't be too difficult. It's minus x over 2t times root t. So we write this, and we've done this before, as minus omega over 2t. All right. Okay. So let's see where we get to here when we do it. So we've got minus omega times phi over 2t ds by d omega plus 1 over root t dq by d omega, and that equals 0. Now what I'm going to do here, may seem a little strange just to begin with, but what I'm going to do is, obviously, that goes here and this becomes a square root. And then I'm going to put this over this side of the equation. And then, in fact, I'm going to write an equation for dq by ds1. Right? And we'll see why we do that in a moment. Okay? So dq by ds1, if we've moved this over this side, we've got an omega of phi over 2. And then what's happened? We've also got a root t term here. Okay, so just bear with me on that one. Now, we now want to solve this equation, and the problem here is that D is highly nonlinear in saturation. Near the end of the video, we'll show you schematically what it looks like, but let's just, mathematically, you can't make any sort of wild assumptions about it simplifying. So what we need to do is we need to think about this inlet condition. If it's a diffusive process, and we've sort of assumed it is here, then we know that distance scales as root t. The amount imbibed scales as root t. So the imbibition rate is the derivative. It scales as 1 over root t. So what I'm going to assume that at the inlet, Q1 star, so this is at here, that the imbibition rate is some constant divided by root t. Now people say, well, yeah, but t equals 0, it's infinite, but it does integrate. Okay, it must scale as 1 over root t in a diffusive process. So this is an assumption, but the interesting physics here is not the 1 over root t. It's a diffusive process. Things move as root t. Rates, right? You differentiate, so it goes down by a power of 1, go as 1 over root t. This is standard for any diffusion process. The key thing is C. What is the rate at which water goes in through the inlet? Now, this is interesting. In the Buckley-Leverett analysis, where I'm injecting water, QT, how much water is going in, is a boundary condition. You set it. You have the pump. Spontaneous imbibition is a bit strange. What it represents is essentially I've got a body of water here, and it imbibes to a capillary pressure of 0. I'm not forcing it in. I don't know the rate a priori. And in fact, the solution is about finding C. It's not a boundary condition. It has to come out of the solution. So rather than getting paralyzed at this stage, I'm just going to say there is a C, and I'm going to find it. The other thing I'm going to define, and it's going to become very clear, hopefully reasonably quickly, why I've done this, I'm going to define a capillary fractional flow. And in Buckley-Leverett we had a fractional flow, didn't we? So that seems to make sense. We can't have a fraction of oil and water flow because actually it's countercurrent flow. So if water goes in, oil comes out, the total velocity is always 0. So that's not going to get us anywhere. But I can define a fractional flow that goes between 0 and 1 as this. I can do as Q1 at some value of saturation here divided by Q1 star. Okay, and this fractional flow will have the nice properties that the fractional flow at the inlet is 1, just as it is in Buckley-Leverett, right, where I'm just injecting water, the fractional flow is 1. This capillary fractional flow is also 1 at the inlet, that's convenient, and that F1 at the initial conditions, we'll assume there's no flow, is 0. Okay, so we got this capillary fractional flow. Now what I'm going to do is I'm going to differentiate. How do I do that? Well, because in Buckley-Leverett, we know that the speed with which the water moves is the differential of the fractional flow, df/ds. So, let's give it a try here, right? Let's see where df/ds gets us. So let's do df1 by ds1. This is a constant, remember, and we know what that is. Okay, so what's on the denominator is Q1 star, which I'm just going to write as C over root T. We sort of know that already. Okay, and then we got dQ1 by ds1. dQ, oh right, It's here, wasn't it? Okay. Oh, and the root t's nicely cancel out. So what have we got here? That cancels out. So we got phi, we got an omega, we got a 2, and we got a c. Is that it? Yeah. Now just a moment. Let's have a little bit of an aside here. When we did Buckley-Leverett analysis, I'll put it up here, right? We said that the velocity with which you moved, and it was a dimensionless velocity, so there were sort of pre-factors, right? Was df by ds. So we knew f, we can differentiate it, we find the velocity. Now, of course, there were shocks, but let me tell you, this is a diffusive process. You do not get shocks in diffusive processes, so it's just a df ds. Okay, v is x over t. Here we scale as x over root t. We got the equivalent here, and it's just proportional to df ds. Okay, there's a porosity term that's popping around. That's just my definition, actually, of d. And there's this constant that we need to find. But mathematically, it looks fairly similar. If I find this fractional flow, all I do is differentiate it, and I find essentially the diffusive speed, the x over root t, with which a given saturation value will move. So I have a saturation, it's going to smear out with a characteristic x over root t that's just given by my derivative. So it's analogous to Buckley-Leverett. It's not exactly the same, it's different physics, but at least I'm exploiting the same sort of idea. So really what I need to do is I need to find f. Basically what we're going to try and do. We're going to try and find f. So unlike Buckley-Leverett where I just write an equation, this capital F I need to find. Okay, so it's going to take a little bit more effort to do. But find it I will. So it's McWhirter and Sonada actually were the first to have this insight into showing that a capillary dominated flow could be replaced by something that looks analogous to Buckley-Leverett. It's not exactly the same. We've got to find this C, right? We need to know the maximum rate. So this we need to find from the fluid properties. But once we know F, we can find omega. And basically that's the diffusion with which a given saturation moves. And I know this sounds a bit weird, but basically we're going to get a saturation profile that's a function of omega. So we're going to have something that looks like this. This is the saturation. This is your maximum. This is your initial. Okay, and we're going to find for a given saturation there's a characteristic value of omega, x over root t. Okay, so that's what we're looking at. C will tell us basically how much imbibed, so sort of the area under the curve. Okay, and F will give us that shape. Okay, so that's what we're going to do next. It's a little bit odd mathematically, but it is quite satisfying. We can replace this rather complex partial differential equation into an integral, which we can evaluate with arbitrary accuracy, and it's an integral over saturation as well. So now we're ready to get stuck in and solve the equation. So let's write it down again. Okay, so what we're going to do is we're now going to write the solution as a function of omega. We've already done this, so I'm going to do it reasonably quickly. I don't want people to worry that I've gone through too much. But if we look here, we're going to change this to a ds by d omega here. And when we do this, we're going to have a minus omega over 2t. And then we do have a porosity term. Here we've got two derivatives. Okay, so that's going to equal, right, minus, we've got a d by d omega, a d ds by d omega. Okay, and there's going to be a 1 over t term, because when I do it once, I get a root t. I'm doing it twice. I'm going to do a root t here. Now let's just think carefully about the signs. Okay, Q is minus D ds dx. Okay, so there's a minus term here, and this equals 0. Okay, so the t's cancel out. Okay, now where do we head with this equation, right, normally? So when this was a linear equation, when we did this for heat transport, for instance, this was a constant. This was actually, we called it alpha. It comes out, and we called ds d omega y. Okay, and we found a partial differential equation for y that gave us a Gaussian, and then we had the integral of this, and we end up with an error function. We can't do this in this case because d is nonlinear. So we need a completely different approach. Well, we've talked about our fractional flow. So we've got a completely different approach here. So we're going to move in a different direction. What we're going to do first of all is we're actually going to integrate this equation once. So we're just going to integrate this equation with respect to omega. Right. Okay, and d omega here. Okay, so here, this first term here is going to be minus, right, omega ds1, and then we got a phi over 2 term, right? Okay, this term, right, d by d omega, this is just the differential of d ds d omega. So this is actually just d ds1 by d omega equals 0. And of course there's going to be some appropriate constant of integration, but we're going to get to that next. So this seems like a problem, but just a moment, we need to think, well, what's omega ds? Now just remember, we just did df1 by ds, right? We did that derivative, and that was proportional to omega, wasn't it? Well, I'm going to get my notes just to make sure that I got the constant of proportionality right here. Okay, so when we did the derivative, it was proportional to omega, and there was a phi over 2c term here, wasn't there? Okay, so that's all we need to know. Okay, so now omega ds, right, if we look at this, is 2c over phi times df. So here, okay, this becomes 2c over phi df1. And the integral of df is just f. Okay, so that's the clever thing. So introducing this fractional flow turned out to be quite a clever idea in the end, didn't it? Okay, so what's going to happen is the phi's are going to cancel. We are actually going to cancel the 2's as well. And we might as well make them both terms positive, right? So here we end up with cf1 plus d ds1 by d omega equals 0. Now, surely there's a constant of integration here, isn't there? Yeah, but let's think about the boundary conditions on f. At the initial conditions, f1 is 0. That was our definition because the water doesn't flow. But just a moment, if the water doesn't flow, d is 0. Later we'll actually write down the equation, but d is proportional to the water mobility. So if the water doesn't flow, d is 0. So when f is 0, d is 0, we don't need another constant, right? There's only going to be one constant, c, in this analysis, so don't worry about that. Okay, so we're getting there, but now we've got a ds by d omega. What do we do? Let's have a look at this one. Differentiating it looked like a good idea first time round, so let's do it again. So let's differentiate this term. So I'm going to get d2f1 by ds1 squared, and I'm just going to call this f1 double primed, right? Double integral. Okay, hopefully that's not too obscure. And then with porosity, and the constant is a constant by sort of definition, this is d omega by ds1. Oh, here we got ds1 by d omega. So ds1 by d omega should be the opposite of that. So it's phi over 2c f1 double prime. Does that look right? Yep. Okay, so let's put that in. So this bit becomes phi over 2c f1 double prime. So we get this. All right, this is looking a bit strange, but let's now move this to here and try and put CF1 and then put something on the other side of the equation. So we got minus phi times d over 2c f1 double primed. So we get f1 double primed is minus phi d over 2c squared. That's a bit strange. I certainly, before I did this, never seen anything like it, but it is an equation for f. And as we've shown, if I know f as a function of saturation, I can basically I've solved the problem. So, it is a bit strange, but the interesting thing is I've started with an equation which is in x and t. This is an equation in saturation space. And that's much easier. I can discretize my saturation between the initial and the S star, which is a measured parameter, with 1,000 grid blocks with arbitrary accuracy. So this equation is an ordinary differential equation, rather strange form, which in principle I can solve. But there's an even cleverer way of doing it. And I know this is going to sound bizarre. Formally, I can write F1 is minus phi d over 2c squared f1 with a double integral, right, with appropriate limits and constants, because f1 double primed is this divided by f1, and then I integrate twice. And you say, I'm sorry about that, but that seems a bit weird because I don't know f1. So how can I find f1 if I don't know f1? Let's think about that a little bit more carefully. But actually, what you can do with this integral is you can think carefully about the limits, and you can integrate by parts, and you can actually end up with an integral like this. Right, and I will this is S1 so this is d of beta. Okay, so let's just explain the terms. F1 is 1 minus phi over 2c squared, an integral here between S1 star and S1. Okay, so this is the lower limit, beta minus SW, sorry, S1, not SW, well it is water, but we'll call it S1. Okay, D is a function of beta, and it's an integral over beta divided by F1, which is also a function of beta. Now, you might say, whoa, how did I get from here to here? So let's just show us what we did. We have to put in a boundary condition so that we know that when S1 is S1 star, F1 equals 1. So there's a constant of integration here, 1, because this integral by definition becomes 0. So that's okay. We integrated by parts, so we replaced a single integral by a double integral, and that's where we emerge with this beta minus s, okay? And it's beta that I integrate over, s actually comes out of the integral. Now you might say, that's a bit confusing, and I'm not going to waste time trying to go through it, because what you should do, that's what you should do in a good partial differential equation, is you've got f1 here, differentiate this twice, multiply them together, and you'll see that it works. Okay, that's how you check, right? That's how you solve partial differential equations. Well, in this case, ordinary differential equations, guess an answer, see that it works. And I'm not going to bore you with going through it. but it does. The other thing you need to know is C, right? And actually we have a boundary condition. We know that F1 at S1i is 0. So if we integrate to S1i, this is 0. So this actually allows us to find C squared, okay, because it's 0 here, right? We go over this side of the equation, and so we can see that C squared, okay, so if I put 0 here, right, then I get C squared is phi over 2 times basically this integral now just to S1i. So it's S1 star, this is beta minus S1, d as a function of beta, d beta over F1 of beta. Now, at this stage, you've got these equations, but they do look a bit, you know, this is looks a bit weird, and in fact you can write F now as just the ratio of these two integrals. How do I go about solving them? Well, actually, what you do is you have to do it iteratively. You have to guess a function f. And the obvious guess is a linear function, and in a subsequent video I'll describe that to you briefly. But basically you have to have a linear relationship. Now you know D. D is related to the fluid properties, so you know D. Okay? You can evaluate this integral. You find a new value of f. You then put the new value of f in here and you iterate. And it turns out you only need to iterate 2, 3, 4 times and you get f with almost machine precision with, say, 1,000 increments in saturation, right? You numerically integrate, okay? Most people, I think, can know how to do this, quite stable, and you actually get your value of f. But you might say, well, this is weird. You've got this weird integral, and you actually have to guess f, then find a new f, and iterate. What's going on here? But it represents the physics. If I have a piece of rock or a tissue or cloth, and I put it in contact with water, it will imbibe. How fast does it imbibe? What's that C? You don't know. It's not imposed. It's the solution. So it is intrinsically iterative. You need to find the imbibition rate and then you can solve. And so it's a sort of, you know, one thing isn't hanging together. So you do have to perform an iterative process. So as I said, I'll describe it a little bit more briefly in a subsequent video. But what I want to do now is actually just show you some example solutions. So let's look at some example solutions. Imagine you've coded up your numerical integration, you've done your iteration, and let's see where you head. So just so that we're clear, we've got a capillary diffusion coefficient, which was permeability, and then these two mobilities, and then a derivative of capillary pressure. So what does that look like? Well, first of all, think about the relative permeabilities. We're normally considering a water-wet medium, right? Because that's where we're imbibing. So the water relative permeability is going to be low, and the other phase, say gas, is going to be much higher. So most of the saturation range, lambda 1 is much smaller than lambda 2. So we said this before, these two almost cancel. The total mobility is actually dominated, say, with the gas, particularly when we encounter viscosity. So this term is principally just a relative permeability divided by viscosity, and that's a phase 1. Now let's look at the capillary pressure. The capillary pressure as a function of saturation does this. This is your S star. This is your initial saturation. This is your S1. This is 0, 0, PC. So we have a gradient that's steep and then shallower where we reach the end point. So let's now think about D. Obviously D does have dimensions of meters squared per second. Right, K has dimensions of meters squared. We've already looked at typical values of that in a previous video, so I'm not going to go through that in terms of orders of magnitude. I'm just going to go through what it might look like. Here's your saturation. This is your initial value. This is your S1 star. So now let's look at how it might behave. Let's consider first a strongly water-wet medium. So say water imbibing into an aquifer that contains carbon dioxide. In this case, actually S1 star is very close to the residual saturation of the displaced phase. And at the residual saturation, actually rather than lambda 2 being large, lambda 2 is actually 0. So we have a case where initially, right, the water doesn't move. So D at the initial conditions is 0, and D here is also 0. So what the capillary dispersion looks like is it goes up and then goes down. So this is water wet. Okay. And we know typical orders of magnitude, right, 10 to the minus 6 meters squared per second for reasonable values of permeability. Okay, so it has this functional form, and it's maximum in the middle where both phases, where you have a reasonable mobility of water, okay, that's S1, okay, of the water, and a reasonable gradient in your capillary pressure. So this is where the maximum is. Now, we have looked at 3 types of wettability. One was water wet, the other was oil wet, right, or hydrophobic, right, not liking water. In that case, there's no spontaneous imbibition, so nothing to do, nothing to see. So if it's hydrophobic, there's no imbibition. But what happens if it's mixed wet? If it's a mixed wet medium, we get typical relative permeabilities that sort of look like this, but S1 star isn't all the way to the endpoint. This is the region in which we have spontaneous imbibition. And a number of things that are interesting here, and actually rather different from the previous videos where we looked at time and length scales. Here the water mobility, the wetting phase mobility, can be really, really low. So this capillary dispersion can have a magnitude that's much, much smaller. We're not imbibing tens of meters in a year, right? We're imbibing much, much, much slower. And this can be many orders of magnitude slower. In experiments, we can have imbibition rates that may be 1,000 or 10,000 times slower than a water wet case. But the other thing is at the endpoint at S1 star, we still have mobile phases. So this isn't 0 here. So S1 star is normally a lower value. We imbibe less, and we end up at a finite value. And we normally find something that is, say, just like this, continues to increase because it's limited by the mobility of the water. So this is mixed wet. Right. So we allow some imbibition. It's normally a lot slower. It's certainly non-linear. The way I've drawn it here, you know, it could be almost linear, but it can be non-linear. It is whatever it is. Okay. Okay. So now let's look at what this means in terms of my fractional flow and my solution. Well, the fractional flow, as I said, it's a fractional flow for a diffusive process. So the fractional flow actually isn't a terribly interesting function. Right? If we got my F1 against S1, this is S1I, this is S1 star, and this is 1. It goes between 0 and 1, but it's always the no shock case. Okay, it's always diffusive. So doesn't have an infinite gradient. It can't have an infinite gradient. And you always have something that looks sort of like that. It's the no shock case. You can't get shocks if you have imbibition. So a little bit more interesting then is omega, which is proportional to dF1 by ds1. And obviously there is this C, which tells me the overall rate that's very much related to D. Okay. So the final plot we'll show here is this is omega, and this will have real units, right? This is x over root t, okay? And this is saturation, okay? And we're going to do 2 cases. We'll do the water wet and the mixed wet case, so this is 0, 0. So let's do the water wet case first. So the water wet, we imbibe to this S1 star, which can be reasonably high. We've got an initial saturation here, okay? So what we see, okay, is, let's think about this physically. Large dispersion coefficient, diffusion coefficient, means things smear out. You get flat profiles. So in this saturation range, we expect to see a sort of flat profile, really smeared out. But at the endpoints, D is 0. D equals 0 means no smearing. That's sort of almost an incipient shock, isn't it? So without going through the mathematics, what this means is there's an infinite gradient here. ds by d omega is infinite. D omega by ds is 0. And it's true actually at the nose here. So what we see is a sort of imbibing water front like that, smeared out at intermediate saturation, and then again a sharp end. So we see something that looks like this. So this is the water wet case. So what we see is not quite a constant saturation, but a sort of water front. So if we do it properly and analytically, what we really see is not quite a flat front moving. It's not a shock case. It is nonlinear. Different saturations diffuse at different rates, but the maximum is here in this saturation that's sort of close to your S1 star. Okay, so that's what you see. Relatively little experimental evidence of this, and this is something that maybe is an opportunity for future work, is actually to measure this saturation profile from which you can find the capillary fractional flow, and in fact you can actually measure the D. Okay, what about the mixed wet case? Well, the mixed wet case, we imbibe less, right? That's the first thing we notice. We imbibe slower. At this point, we have an infinite gradient, but not here. It's finite, right? There's a finite spreading. Okay, and in fact, if anything, it's finite and then it's just getting sharper like that. It's getting less and less spreading. Okay, and then the saturation looks like this. But the main thing with the mixed wet medium is actually the total amount imbibed, the sort of area under this curve, can actually be a lot less than the water wet case. And it may be a lot less by orders of magnitude. And the reason is physically, is the imbibition in a mixed wet case is limited, very limited, because there are only a few regions that are water wet. And the water has to imbibe, has to sort of move through regions in the corners of the pore space, which are hydrophobic, and these are pinned layers. And so the water mobility is enormously restricted. So for instance, imbibition in a mixed wet oil field, even a mixed wet oil field where CO2 has been present, can be really, really slow. Okay, so the imbibition process can be slow in a more mixed wet case, and that would be same if we reverse it, if we have CO2 imbibing into an oil field. Actually, that imbibition rate can be very slow. If it's strongly water wet, so we're looking at more sort of water gas system in an aquifer, it can be rapid and we get this sort of almost front-like behaviour. But the beautiful thing is, with some rather unusual mathematics that you almost certainly haven't met before, with this curious iterative integral, okay, we can actually derive these profiles, and you can evaluate them basically with arbitrary accuracy. You can discretize your fractional flow with, say, 1,000 saturation points. You can find this derivative really accurately, and you can find nice, smooth, as I said, arbitrarily accurate solutions.